presentation. I'd like to introduce Kasia Tushinska, who will be your presenter today. Kasia?
Good morning. My name is Kasia Tushinska, and I'm an instructor with the training team here in Redlands, California. Joining me today is Sheila Ferguson, who is an educational specialist with the Virtual Campus. I want to welcome all of you to today's live training seminar, Working with Geodatabase Precision and Spatial Domain. The properties of precision and spatial domain define how data is stored in a geodatabase. You will interact with them as you're populating a geodatabase. So for the first topic of this seminar, let's take a look at some of the tools and dialogues that you can use to bring data into a geodatabase and where you would interact with precision and spatial domain as dialogues. Then, we will introduce precision and spatial domain conceptually. We will talk about what they mean, their defaults, and best practices. Each session will be followed by a demonstration, review, and a Q&A session. So let's introduce the environment in which a geodatabase is populated. Geodatabases are organized into feature datasets and feature classes. A feature class is a collection of like features, a source of data. For instance, you could store all of the streets in Redlands in which ESRI is located in one feature class, or you could store a political map of the world in one feature class. Each feature class will have information associated with it about its geographic projected coordinate systems, as well as how data should be stored in a geodatabase. That set of information is called spatial reference. On the slide, you see a snapshot of a personal geodatabase and an enterprise geodatabase, populated with the same data for comparison. Both have three feature classes: the cities feature class, the country feature class, and France feature class. Notice, however, that the cities and country feature classes are grouped together under countries. Countries is a feature dataset. A feature dataset is used to group feature classes that have the same spatial reference. So the cities feature class and country feature class inherit their spatial reference information from country's feature dataset. The France feature class is called a standalone feature class because it is not part of a feature dataset, and its spatial reference information is defined on the feature class level. We will be using the France feature class as an example throughout this seminar. In order for spatial data to be appropriately stored in reference to a location on Earth, it must have a spatial reference. So a spatial reference is stored for every feature class, either standalone or grouped into a feature dataset. It defines which geographic coordinate system the data is in, and if it was projected, then the projection that was used. Anyone who has worked with geographic data is well acquainted with this type of information. On this slide, you see the geographic and projected coordinate systems for a shapefile of France. If you're interested in more information on projections, I highly recommend one of our earlier live training seminars on projections. But spatial reference additionally contains information about how this feature class is supposed to be stored in the geodatabase. How data is stored is indicated by precision and spatial domain. Precision is a numerical value supplied to the geodatabase that preserves accuracy of the data in your feature class. It preserves how fine your data is. It is accurate to a meter or a millimeter. Spatial data is a set of bounding x and y coordinates that determine the space in which a feature class resides. These coordinates determine a location of a feature class within a limited coordinate space. Precision and spatial domain can be defined by you, or you can choose to let the system calculate them for you. They're supplied to the geodatabase as data is being brought into the geodatabase, and once you use those values and data is stored in them, they cannot be changed. So precision and spatial domain are properties that control storage. They're part of spatial reference, which is indicated when data is imported. So let's take a look at some of the tools that you can use to populate a geodatabase. And we're just going to take a look at a couple of them. There's not enough time to show you all. There are tools in ArcCatalog for creating new data, importing data, or exporting data into a geodatabase. ArcToolbox contains over 400 geoprocessing tools, some of which are used to populate a geodatabase, and we will examine the conversion toolbox and the data management toolbox. There's also the object loader in ArcMap, which we unfortunately will not have time to cover. And if you're working with a enterprise geodatabase, there's some command line tools available to you as well. Each of these tools will give you an opportunity to determine precision and spatial domain. ArcCatalog is probably the most prevalent tool for populating a geodatabase. If you right-click on a geodatabase, so Canada in this case, and go to New, you can either create a new feature class or a new feature data set. Or you can import data that already exists in an electronic format, such as shapefiles, coverages, or CAD data. So in this case, I right-click on a personal geodatabase, click Import, and I can use the feature class single tool or feature class multiple tool, with which I can import several feature classes at the same time. You can also right-click on the shapefile, so in this case my shapefile of France, to be exported into a geodatabase, and use the toGeodatabase tool, single or multiple, to bring data into a geodatabase. ArcToolbox is a dockable window in both ArcMap and ArcCatalog. It is a group of geoprocessing tools, and among them there are several tools that are used to either import or create data in a geodatabase. What you see on this slide is the conversion toolbox. Under toGeodatabase toolset, you have the feature class to feature class tool. This converts data from one spatial format to another. The feature class to geodatabase multiple tool, which allows you to bring over multiple files to feature classes all at once. In the data management toolbox, under the feature class toolset, is the create feature class tool, which creates an empty feature class, and under the same data management toolbox but under the general toolset, you have the append tool, which adds data to an existing feature class. So lots of tools and scenarios through which data can reside in a geodatabase. We mentioned earlier that each of these tools will allow you to set precision and spatial domain. And there are two types of dialogues. You will find that the dialogues for setting precision and spatial domain look a little bit different, depending on if you're creating a new empty feature class or feature data set, or if you're importing data into a geodatabase. This is the dialog that you will see when you're creating a new empty feature class. And this is the dialog where you can set precision and spatial domain as you're importing data into a geodatabase. Both allow you to set the same properties, they just look a little bit different. These dialogues is where you would specify either your own values for precision and spatial domain of a feature class, or you can let the system calculate default values for you. Later on in the seminar, we will touch upon default values for both new feature classes and feature data sets that are being imported. I'm going to do the simplest thing possible. In my first demonstration, I'm going to import a shapefile into a geodatabase and let the system calculate default values for me. So I'm going to go to my ArcCatalog, and this is my shapefile which I will be importing into the demonstration geodatabase. So let's take a look at the shapefile first. This is what it looks like. Very simple shapefile of France. The metadata for this shapefile resides under the Spatial tab. As you can see, we have the projected coordinate system and the geographic coordinate system. I'm going to right-click on the personal geodatabase. I'm going to click Import. And I'm going to use the multiple tool just to show you that you can bring over multiple shapefiles into a geodatabase all at once. So my destination has already been established. It's the demonstration geodatabase. I'm going to search for my shapefile. Here it is. Click Add. And even though I'm going to accept all of the defaults, let me just show you where they reside. So I went to Geodatabase Settings, and this is where I would set my domain and precision. But since I'm taking the defaults, I'm just going to let it to default as same as input. Click OK. Click OK to accept the process. And now that process is being done, as you can see, I can see all the stages of this process. If I were to incur any problems, that would be highlighted for me in red. I'm going to click close, and let's take a look at my newest feature class. So this is my friends feature class. Let's preview it. Looks very much the same like the shapefile. And to prove it to you, let's take a look at the metadata. And as you can see, all of that information from the shapefile was brought over. But let's see what were the default values for precision and spatial domain. I right-click on the feature class, on the new shapefile, went to Properties. Under Fields tab, I'm going to go to the Geometry field, expand that. And as you can see, Spatial Reference is populated. I'm going to click the ellipsis button. And this is my spatial domain and precision information. So these are my default values determined for me by the geodatabase as it was loading that shapefile. Click OK. Click OK to close. And let's get back to our presentation and go through a little bit of a review. In this first topic, we talked about the fact that geodatabases can be organized into feature classes and feature datasets. Spatial reference information can be defined on either feature class level or feature dataset level. Spatial reference contains information about coordinate systems as well as properties that define storage for the data in a geodatabase, such as precision and spatial domain. Precision preserves accuracy of data. Spatial domain is a space in which a feature class can reside in a geodatabase. We also looked at tools in ArcToolbox and ArcCatalog. Now, let us give you an opportunity to ask us questions, so I'm going to turn it over to Sheila.
Thank you, Kasha. All right, we already have a number of questions, and quite a few of these questions Kasha will be covering later on in her presentation. But let me go ahead and answer a few of these questions. Keith from Madison, Wisconsin. Do precision and spatial domain need to be defined for feature classes that I'm converting to a geodatabase? Well, Keith, you can decide that you are going to set particular values for your precision and your spatial domain based on the needs of your data. However, as Kasha just showed you in the demo, you can also allow the software to choose those default values for you. And she'll get into that a little bit more later on in the presentation. Jim from Jacksonville, Florida. Can I change the precision of a feature class in a feature dataset? And remember that the only time that you can change your precision is when you're creating a new feature class, or when you are importing data into a feature class, or when you're creating a feature dataset. And that is when you can change the precision. And remember also that all feature classes in a feature dataset inherit the precision of the feature dataset. Okay, Kasha, I think some questions that you wanted to take care of?
Yeah, sure. Actually, I have a question here from Carmen from Roanoke, which is a very, very good question. She asks, what happens when you go from a personal geodatabase to an enterprise geodatabase? Do I have to reload all of my data? Well, Carmen, absolutely not. Personal geodatabase is completely scalable to an enterprise geodatabase, meaning that whatever you created on the personal geodatabase can be just dragged and dropped into an enterprise geodatabase. There is no reload. None of that headache at all. It's simply a drag and drop or a copy and paste. Very, very simple. I have a question from Dog from Boston that asks, is the spatial domain always a rectangle? Dog, we will cover this in the third part of the seminar, but to give you a very quick answer, it's always a perfect square. But just to titillate your interest for the third part of the presentation.
Okay, and we have a question from Sandy from Atlanta, who asked, the default precision is usually going to be more than enough to preserve the data, correct? And that is quite correct. Very often you will find that the precision by default is set quite high when you're importing data, and that it will certainly more than meet your needs. Again, this is something that Kasha will be getting into later on into the presentation about setting your precision. Are there any problems with setting it too high or too low? The other thing to sort of consider is depending on whether you're creating a new feature class or you're importing data, you're given different default values, and Kash will be explaining that a little bit later in the presentation. Okay, I think that's probably about it for questions for right now. We'll be getting back to the presentation. Kasha?
Thanks, Sheila. All right, so in this first part of the presentation, we saw that taking defaults is very easy. The geodatabase does a very good job of providing us default information. But what if you had to calculate these values for yourself? The very first thing we're going to take a look at is the property of precision. We know that precision is set for either feature datasets or for individual feature classes. We also know that precision determines storage in the geodatabase. That precision is a way to let the geodatabase know what is the accuracy of your data. Now, what do we mean by all of that? Let's track back a little bit. When you hear the word precision, you might be thinking of precision as it is used in the shapefile or coverage world, where data was stored in a single or double precision data type, single or double precision. Geodatabase precision has a very different definition. The geodatabase uses an integer to store coordinate values. It uses a signed integer data type, which is able to store coordinate data with values up to 2.14 billion. And you see that number right here. Why does the geodatabase use integers to store coordinate values? The very quick answer is performance. Integers allow for faster processing. It is easier for the CPU to process positive whole numbers rather than decimals. Storing coordinate values as integers also helps out with the amount of storage used, because the geodatabase ends up using less physical disk space. And it helps out with coordinate geometry. So, as data is collected, it is done so with a particular accuracy. Accuracy depends on the instruments with which data is collected. On this slide is an example of the same set of points gathered with different GPS units. The first one is a commercial GPS unit, which is able to provide data with the accuracy of about 2 centimeters. So pretty accurate. As opposed to the example on your left of a GPS unit that I could purchase at a sporting goods store, which can only collect data with an accuracy of, let's say, 10 meters. Both of these GPS units can give you coordinate values with many significant digits after the decimal. But because of the sensitivity of these instruments, some of these numbers may be meaningless. The question that should be in your mind right now is, if the geodatabase uses integers to store coordinate values, and you know that for the most part, coordinate values are a decimal number, then how will the geodatabase accommodate a decimal number using a whole number data type? Okay. The answer is multiplication. If you multiply a coordinate value by a number large enough, you can preserve the significant digits after the decimal and store it as an integer. The example on this slide is that of a number with 3 significant digits after the decimal. When it is multiplied by 1,000, I can preserve those values. So the value of 1,000 is the geodatabase property of precision. Precision is a value supplied to the geodatabase to indicate the actual accuracy of your coordinate values. Precision will be used by the geodatabase to multiply your coordinate values to preserve significant digits after the decimal. How would you determine precision if you wanted to set it manually? As an example, let's determine the precision for our shapefile of France that we've been using as an example. The very first thing I'm going to do is take a look at the metadata for this shapefile. What you see on this slide is the spatial reference information as seen in ArcCatalog through the metadata tab. So we have already seen these in the demo. The projected coordinate system, geographic coordinate system. And if I expand the details tab right here in blue, in green, then I will know that my data is in meters. On the lower left-hand side, I see the maximum and minimum x and y coordinates for this data. These are also known as bounding coordinates. They're kind of hard to see, so I've put them on this slide right here. So these are bounding coordinates for this shapefile. Now let's take a closer look at them. We know that data is in meters, and these are our bounding coordinates. So if we specify a precision of 1, no significant digits after the decimal are preserved, and our data is stored with an accuracy to a meter. A precision of 10 would preserve 1 digit after the decimal, so the data would be stored with an accuracy of a decimeter. A precision of 100 would preserve 2 digits after the decimal, preserving centimeters. And precision of 1000 would preserve 3 digits after the decimal, storing millimeters. 6 significant digits after the decimal indicate an accuracy of a micrometer or 1,000 of a millimeter. Most likely your data is not accurate to that degree. I'm going to choose to store my data with an accuracy of a millimeter, preserving 3 significant digits after the decimal. To do so, I will indicate a geodatabase precision of 1000, which will be used by the geodatabase to internally multiply the coordinate values to preserve those 3 significant digits. I want to point out that no matter what precision you're going to choose, the geodatabase will round up your coordinate values. The numbers that you see in red, so for instance this 2 right here, have been rounded up and their values have been changed as a process of rounding. So there was an additional number behind it, and that contributes to the rounding up or rounding down of this value. So the last value is always rounded. Because of the occurrence of rounding, there's a danger in not storing your precision high enough. Generally, we recommend that you specify the precision higher than the actual accuracy. So if you want to preserve millimeter accuracy, even though 1000 is the correct precision value, you could use the precision of 10,000 to make sure that the rounding occurs on the 4th digit after the decimal. So a number that you're not interested in preserving anyway. 2 things can happen if your precision is set too low. Data can quote-unquote jump around, meaning that the location of your features can shift, or features can become generalized. You see that on this slide, actually. As the precision of this feature class decreases, so goes from 100 to 10 to 1, my feature is generalized. It loses its details. Setting your precision too high does not carry such consequences. You may want to be lured into believing that storing data with higher precision will make your data more accurate. Not so. In actuality, if the data was accurate to a meter and it is stored with a precision of 1000, you are just taking up more space for data that is only trustworthy to a meter. Now, there should be another question in the back of your mind. If the coordinate values are multiplied by the value of precision, am I, as an ArcGIS user, going to interact with multiplied values? And the answer is no. Coordinate values are only stored as integers. As those values are requested by the user application, such as ArcMap or ArcCatalog, before sending it out, the geodatabase will divide those values by precision and then serve them to ArcMap, for instance, in a decimal format. And vice versa. As you save data in a geodatabase, it will then multiply the coordinate values for storage. So you, as a user of coordinate values, will never interact with them in the multiplied form. Let me give you some guidelines for when you're thinking of storing data. If your data has been projected, meaning that your coordinate values are in map units such as meters or feet, your precision should be anywhere from 1 to 1000. If your data is in geographic coordinate system and coordinate values are stored in decimal degrees, indicated by the absence of projected coordinate system in the metadata, your precision should be at least 1,000,000, preserving 6 significant digits after the decimal for seconds, minutes, and degrees. Of course, you may want to use higher values in consideration for rounding. We have just spent a lot of time talking about the importance of precision. But I want to caution you that considering precision exclusively when bringing data into a geodatabase will earn you a lot of frustration. In the following demonstration, I'm going to again import the shapefile of France and change only the precision. And you will see that my import will be unsuccessful. So I'm going to go back to ArcCatalog. And again, this is the shapefile in question that we're going to bring into the geodatabase. And I'm going to right-click on the personal geodatabase, click Import. Again, use the multiple tool for consistency. Browse to find the shapefile of France. Click Add. Going to go back to the Environments tab, Geodatabase Settings. Scroll down to my Domain and Precision dialog. And I'm going to say, as specified below. The default values that you see are what the tool provides. You can think of them as placeholder values. They are generated regardless of the data, meaning that they are not provided considering the data. They're just there. So I'm going to come back here and put in a precision of 1000. I'm going to click in one of these boxes, and I want you to pay careful attention and notice that these values, the maximum y and the maximum x, have adjusted to the precision. This is very important because precision and spatial domain are related. So every time I change precision, it's going to affect my spatial domain, and sometimes vice versa. So I've changed my precision. I'm going to click OK. I'm going to click OK to start the process of importing. Now, if you recall from the last demonstration, I mentioned that if there is anything to go wrong, this dialog would show me something in red. But we're not seeing anything in red, right? I'm going to close, and let's take a look at our new shapefile. And our shapefile is empty. So as I mentioned, this is not going to work. Just changing precision is not going to work. But our dialog did not show us anything in red, because technically a feature class has been created, so the process of importing has been successful, except the values that we have supplied for this feature class were not correct, and therefore the feature class was created, but the data itself did not make it. Now I'm going to go back to our presentation, and now it's time for me to ask you a question. If you'd like to participate, find the review question link in the upper left corner of your browser. Click on the review question link, and you should see your answer choices. Once you've selected your answer choices, click one of the choices and click Send. So let's see what the question is. If your data is in feet, but you would like to store the precision at an accuracy of 1 inch, what would be the value of your precision? To answer, please click A, B, C, or D, and then click Send. In the meantime, let's do a bit of a review again. So in the second part of the presentation, we've talked about the difference between geodatabase precision and precision as it was defined in the shapefile and coverage world. Geodatabase precision is a multiplication value for your data to preserve its accuracy. Accuracy, we mentioned, is determined by how the data was gathered. So sensitivity of instruments, things of that sort. So as you know that your data accuracy, you choose a precision to appropriately preserve the decimal spaces after the significant digits after the decimal. You indicate that. You determine that by actually looking in the metadata of your shapefile and knowing a little bit about your data. We also mentioned that there is a danger in storing too low of a precision, meaning that your data, if it doesn't have enough precision, may jump around, may melt into one another. Your features may melt one into another. We also talked about that coordinate values are multiplied by the precision and they're stored as such, but you as an ArcGIS user will never interact with them in that multiplied form, so you will always interact with decimal numbers. And we talked about some precision guidelines depending if your data is projected or not. So I'm going to turn it over to Sheila again for another round of questions.
Okay, thank you, Kasha. Okay, we have a question here from Bruce in Boise, and he said, if my data only has accuracy to the meter level, is there any advantage or disadvantage to setting precision to the centimeter level? And there are at least a couple of advantages I can think of off the top of my head for setting your accuracy, if it's accurate at the meter level to the centimeter level, your precision rather. One Kasia touched on, which is there is a problem with rounding, that if you don't have your precision set high enough, you may run into problems because of when the number is converted, when your coordinates are converted to integers. So in this case, you would want to be able to set your precision a bit higher. Another reason you might want to set your precision higher is if you're working with a feature data set. Remember, the precision applies to all feature classes in the feature data set. And perhaps right now, all of your feature classes are at your accuracy is at the meter level, but later on you might be getting data in that is accurate to the centimeter level. You're going to have feature classes that are at that accuracy, and you want to be able to preserve that accuracy without having to recreate that feature data set and change the precision. Okay, Steve in Las Vegas. I thought that the bounding coordinates couldn't be negative values, but one of your slides showed the dialog with values of 1,000, and what's happening here? Well, remember, this is the difference between how your data is stored in the geodatabase, what's kind of going on behind the scenes, which is storage in integers, positive integers, versus what you're seeing on your screen when you're working in ArcCatalog or ArcMap. And what you're always going to be seeing is with decimal places and with either positive or negative numbers, depending on where your data is located geographically. Okay, a question from Charlie in Houston. Can a standalone feature class have a different precision than a duplicate feature class in a feature data set? And yes, they can, because you set the precision and the spatial domain for standalone feature classes, and you set it for a feature data set. And so those could be different. And another question, this one from Julie in Ann Arbor. Are you saying that if I convert my coverages to a geodatabase, I don't have to worry about maintaining double precision? That's correct. One of the advantages about precision in a geodatabase is that you have control over that. You decide what level of accuracy you need to preserve, and then you set your precision value to preserve that level of accuracy. And these are always integer types rather than single precision or double precision data types that you're familiar with in shapefiles or coverages. So again, we're dealing with a little bit different definition of precision here. You know, always think about what's the accuracy of my data that I need to preserve, and the precision value is how that accuracy is going to be stored. Kasia.
Thanks, Sheila. I actually have an excellent question here from Flora from Manchester. And Flora asks, can we expect a bigger integer value? Because right now we're working with a 32-bit integer value, which gives us that limit for our coordinate values that can't go beyond 2.14 billion. Can we expect a 64-bit integer? And the question is absolutely yes. We're currently developing code. We do not have a release yet, but we're working on it at the moment about providing 64-bit integer for storing coordinate values instead of the 32 that we currently use. And what that would mean for us as users of this software is that the limitation for spatial domain would be in quadrillions. So incredibly huge number. It would change a little bit the way we think about these problems. I think it's time to see how we did on our question. And I see from the poll that most of you got it. That's excellent. So the correct answer was B, but let's go back to the question. So the question was, if your data was stored in feet, but you would like to store the accuracy to an inch, what would be the value for precision? And the way to think about it is how many inches are there in a foot? The answer is 12. And it looks like almost 75% of you got the correct answer. Excellent. In reality, we would recommend that you use the value of 120 just for those rounding purposes. Now, let's talk about our third topic. You saw in the third in the previous demonstration that if you choose to supply your own values for precision and spatial domain, that they are related, that you cannot supply a value for just one. And you also saw that when I changed the precision, that the values for the spatial domain adjusted. So, and we know now that both values have to be considered. So let's talk about spatial domain. What is it? Technically, we can define spatial domain as the maximum coordinate space in which data can reside. As you recall, the integer data type in which your coordinate values are stored has a limit of 2.14 billion. And you see that value again on the slide right here. That is a huge number. Nevertheless, you need to test if your coordinates multiplied by the precision exceed that limit. For the ease of explanation, let's think about it visually. The location of the features that make up your data are designated by the value for the x part of your coordinate and a value for the y part of your coordinate. Imagine that the y-axis represents all of the possible values for the y part of your coordinate, and the y and the x-axis represents all of the x values possible for your coordinate. Since a coordinate has both an x and a y, we will be essentially plotting this on a grid. This grid does not exist. It is a virtual or an imaginary grid. We call it spatial domain or coordinate domain, and it is the allowable coordinate space in which your feature class can reside. Given the multiplication of coordinate values by precision, do any of your coordinates exceed the limit of 2.14 billion, meaning if I take a coordinate value multiplied by my precision, is the value that is multiplied larger than the number that you see on the screen? If so, then you exceed that limit and your data will fail, just like my demonstration. In essence, we will be testing if your features fit inside of the spatial domain. If you recall in the last demonstration, that is precisely what has happened. I supplied incorrect numbers and my data did not fit inside of the spatial domain, therefore it was simply not placed in that feature class. So let's go ahead and place the France data into the spatial domain with a precision of 1000. This is how our data looks for France with, in the spatial domain with a precision of 1000. If you look at how the coordinates were rounded, they were rounded at the third significant digit after the decimal. A precision of 1000 means that each of these cells in the grid is storing 1 millimeter of data. So a meter is stored in 1,000 of those cells. We're storing a lot of precision at this, a lot of detail at this precision. On your right, however, you see the same piece of data stored at a precision of 1. That means that the coordinates were rounded to the whole number. No significant digits after the decimal were preserved. A precision of 1 means that 1 meter of data is stored in one cell. The most important thing to remember about precision is that the higher the precision used, the less data can be stored in that spatial domain. What that means is that if my study area is the country of France, and I will not be adding information about any other country, then this is fine. But if I would also want to store information about France's neighbors, such as Spain, Switzerland, or Belgium, I would run out of coordinate space. If I choose to store France with a lower precision, for instance 1, right here, then I would have enough space for Spain, Switzerland, and Belgium. Now, what you see on this slide is a huge exaggeration for the purposes of an example, just so we can visually grab an idea. In actuality, you could store about half the world at a precision of 1 centimeter in one feature class in a geodatabase. So when we say check your precision, we mean to make sure that the values of coordinates with the chosen precision do not exceed the 2.14 billion limit. The aim is to have enough space around the data to be able to add features such as Spain or Switzerland. In the very first example that you see on this slide, the precision is calculated well. It fits into our spatial domain. It has enough room to expand geographically if necessary. So if I wanted to work with Spain, I would have enough room here to include that. In the second example, the precision is too large. The bounding coordinates after being multiplied by the precision are larger than the 2.14 billion. And you can also see that visually because France is definitely larger than the allowable spatial domain. In the third example, the precision is correct. However, the location of the data is outside of the spatial domain. This third example is actually something that some editors in the audience may be acquainted with. If you have ever found yourself editing a feature class and you are trying to create a feature, so I was trying to create a feature right here in my friend's feature class, and then all of a sudden I got this error. The create feature task could not be completed. The coordinates or measures are out of bounds. This means that you're trying to create a feature outside of the spatial domain of this feature class. In order to solve this problem, you would have to either relocate this feature class, meaning that I would have to recreate it, create a new feature class, and change either the precision or shift the data. Shift the spatial domain around the data. What do I mean by that? This is my problem. So in the error that I have incurred means that I was trying to create a feature perhaps right here, definitely outside of the spatial domain as it is indicated by the gray box. These are the values for my spatial domain at the moment. So these values correspond to these points. What I'm going to do is take this gray box, shift it up and to the right to fit around my data. If you noticed, the values for my spatial domain have changed, meaning that I have precisely done that, just shift the spatial domain to fit well around the feature class. Now, I know some of you may be wondering, what has just happened? Did I just reproject my data? Where either the geographic or projected coordinate systems changed? No, the data itself did not move at all. What has moved was that gray box. What we've done is to relocate the internal space in the geodatabase available to store the data. Let's talk a little bit about the spatial domain in general. Because processing with positive numbers is faster, we only work in the positive quadrant of the spatial domain. In the beginning, we defined the spatial domain as the maximum possible coordinate space in which data can reside, and that you see in the blue box. That is our gray area. The amount of coordinate space that a feature class takes up is known as an extent, and that you see in the red box. Now, you may be asking yourself, how do I make a decision about storing a feature class? There are three ways in which this can be approached. If you have a feature class that covers your entire study area, then import that feature class and accept the default values for spatial domain and for the spatial domain. The defaults will create a domain that encompasses all of the features with a little room to grow. Look at the default for precision and make sure that it preserves your accuracy. Use that spatial reference information from that feature class for all other imports. If you do not have one feature class that spans your entire study area, then determine the X and Y bounding coordinates for your entire area of study, and then create an empty feature class with that spatial reference information. Again, make sure that the precision and defaults are acceptable to you. Use these settings when you import any additional data. You could also calculate both precision and spatial domain, keeping in mind to set the precision about 10 times smaller than the best accuracy, meaning that if your best accuracy is centimeters, then store it with a precision of millimeters. If you're thinking of this approach, there are plenty of sources of help, including our help documents or classes that can guide you step by step. It's also a good idea to test a couple of these scenarios. The worst thing that can happen is that if your precision or extent are too large for you, and your study area will end up residing in 2 feature classes. So not that bad. Let's talk about the defaults. If you're creating a new empty feature class, you will notice that by default, spatial reference information is unknown. If you wanted to associate a spatial reference information for this feature class, click on what we call the ellipsis button, and that will lead you to the appropriate dialog. If you're creating a new feature dataset, so a logical container for feature classes that share spatial reference, again, by default, that information is blank, so unknown coordinate system. You can click on the edit button, and that will lead you to the appropriate dialog. In both cases, the appropriate dialogs are almost identical. You can define the precision and spatial domain. The values that you see in these dialogs are defaults. The geodatabase does not know what kind of data will be stored in these objects, so it is trying to do an educated guess. The precision is 100,000, so okay for data in both feet or meters and in decimal degrees. And given that precision of 100,000, the values for spatial domain will place your data right about in the middle. So this is when I'm creating new feature classes or new feature data sets. The defaults will behave a little bit different when data is imported. So if you take a default like I did in the first demonstration, the geodatabase will consider the extent of the data and calculate the best spatial domain. So there's a buffer for adding features. It will also let the precision default. This is why when you look at the default values sometimes, the precision may be in a rather unusual number like 1736, for instance. That is because the default precision was determined by the best fitting extent. You could choose the as specified below option to provide all of your own values. You could also do a little bit of a trick. If you wanted to see what the default values would be and adjust them just a bit, maybe define the precision to 2000 rather than 1778, you could make sure that the data is active. So my feature class of France is active in the catalog tree. Preview it in ArcCatalog and choose a tool to import. And if you look in the pull-down menu for the domain, you'll see an additional option, same as display. This will bring the default values into the dialog, and you see them in the gray box right now. Then go back to as specified below, and those values will become available for you to work with, and you can adjust them just a little bit if you like. Now you're probably wondering if each time you create or import a feature class into a geodatabase, will you have to define the spatial reference information? No, absolutely not. In all probability, you're going to have to define it once, and then you can use that information over and over and over. So if you're creating a new feature class or feature data set, you could click the import button. So this is creating a new feature class or feature data set. I'm clicking the import button, and I get this browse dialog. And I can browse to any feature data that already exists that has the appropriate spatial reference information that I'm interested in. You can do something similar in ArcToolbox. I can right-click on ArcToolbox and go to Environments. These are global environments, meaning that I can set arguments for all of the tools that I will be then using in ArcToolbox. I only have to set it once. But if I'm using a specific tool and I didn't set my global environments, as I'm using that tool, I can also click and browse and grab a browse dialog and also search for spatial reference already predefined on a feature class. Actually, let me show you how to do that. What I'm going to do, I'm going to create an empty feature class and associate an already defined spatial reference with it. And then I will import actual data into my feature class. So first thing I'm going to do is create an empty feature class. I'm right-clicking on my personal geodatabase. I'm going to click New. I'm going to click Feature Class. And let's call it France 3. Click Next, accept the defaults. And now I'm going to go to my geometry under Data Type, expand that. As you can see, the spatial reference is unknown. I'm going to click the ellipsis button. I'm going to click Import. And go to Western Europe, which is my study area, click Add. And now as you can see, that information is populated for me automatically. The spatial domain and precision are automatically populated. I don't have to worry about it. Just going to click OK. Going to click Finish to start the process. And here is my empty feature class. As promised, it has absolutely no data. So now we're going to populate this feature class. I'm going to right click on it. I'm going to say load. I'm going to use a simple data loader. We have not met this tool before because it does not allow you to change anything. It just loads data. I'm going to browse to my shapefile, click open, add it to my process, click next, accept all the defaults, click finish. This is what my study area looks like. This is what my new feature class looks like. Let's go to the study area and take a look at the properties. Geometry. So these are the properties that I've imported. You've already seen these values. Same for my France. Now, remember that the spatial reference information contains not only how data is contained in a geodatabase, but also the geographic and projected coordinate system. So now France is in a different geographic and projected coordinate system. I think we're going to go back to our presentation and do our last bit of review. In this third part, we talked about the fact that spatial domain and precision are related. Spatial domain is the maximum coordinate space in which your data can live, meaning that if I take my bounding coordinates and I multiply them by precision, they define that spatial domain. If I'm trying to create data outside of this predefined spatial domain, I will most likely get an out-of-bounds error while editing. There are a couple ways in which I can solve that issue. All of them involve recreating that feature class, and one way of solving it is to actually shift my spatial domain, so to supply different values for the minimum x and minimum y coordinates, so my spatial domain will fit properly around my data. We talked about guidelines for choosing spatial domain. There is about 3, and that depends on what your situation is. If I have a shapefile that encompasses my entire study area, I can use that spatial reference information. If I don't, I will have to calculate that spatial reference. But then once that is established in one feature class, I can use it to import over and over and over. So in reality, you really have to establish it once. So let me give you an opportunity to ask us questions. Let's turn it over to Sheila again.
Okay, thank you, Kasha. All right, first question is from Christopher in Meadville. Can a feature class within a geodatabase be projected into another projection after the precision and domain have been set? Yes, that is the part of the spatial reference. Remember, when you go into that dialog, there's a spatial reference dialog, and there are 3 things affected there: the coordinate system, the precision, and the spatial domain. And the projection, the coordinate system, is the only part of those 3 things that you can change after you've created your feature class or your feature dataset. Okay, a question from Dan in Greeley. Can I shift the spatial domain after it has been defined? No, because that's changing the spatial domain, and you cannot change the spatial domain once you have finished creating your feature class or importing the data into the new feature class. What you would need to do if you decided, oh, it doesn't fit and I need to change this, I need to shift it, is you would need to import your data into a new feature class or create a new feature data set and move your data into that. Question from Bob in Baltimore. Does a higher precision geodatabase take up more disk space? And yes, if you're storing your data with higher precision, that does take up more storage space on your disk. Question from Karen in Centennial. Can you go back and see what you set your precision at after you already set up your geodatabase? Yes, you can. once you've set it up, you can always go back and look at the properties for the feature class or the properties for the feature dataset. And what you do is you would say for in the catalog tree, right-click on that feature class, go to Properties, it pulls up the Spatial Reference Properties dialog, and you would click on the XY domain tab, and you can see what your spatial domain, your minimum X, minimum Y, and your precision that you have set it at. You can't change it, but at least you can see it. Okay, Kasha, a couple of questions for you.
Yeah, absolutely. I have actually a couple questions that are related, or they're pretty much asking the same thing. Question is, do I have to delete my entire geodatabase to start over if I have imported a shapefile feature class with the wrong precision? And that is a bit of a misconception, because the precision and spatial domain are properties of a feature class, meaning that every feature class in your geodatabase can have different precision and spatial domain. You absolutely do not have to delete a geodatabase if one feature class has been imported with incorrect precision and spatial domain. Just simply delete that feature class and start over again. And a related question, I read that precision and spatial domain are properties of the geodatabase. Again, they are properties of the feature class. They can be different for every single feature class in a geodatabase. And looks like we're out of time, so let's talk. If you're interested in more information, there's actually lots more information out there. We have information on the virtual campus. There is a class called Creating, Editing, and Managing Geodatabases for ArcGIS 9. There's also a previously broadcasted live training seminar about projection. So if you're curious about how projection affects your spatial domain and precision, that is an appropriate place to go. There's also some instructor-led training introduction courses to ArcGIS 1 and 2 will discuss precision and spatial domain. Building Geodatabases courses 1 and 2 will also touch upon the subject. And if you take any of our administration courses for ArcSDE, we do have a section on spatial domain and precision as well. On behalf of ESRI, I would like to thank you all for attending.